This is the 7th video in a series devoted to introductory proofwriting, and we're doing a couple of videos related to counting. So we just made a video on the multiplication principle, the addition principle, and the subtraction principle, as well as k permutations of n elements. And now we're ready to look at subsets of sets within elements and all of the counting that goes along with that. So let's look at our main definition for the day, and that is n choose k, or the binomial coefficient as we'll come to know it a little bit later. So if n and k are integers, then we'll define this symbol right here, which we will read, like I said, as n choose k, as the number of k element subsets of an n element set. So I think that gives you some idea for why we're using the word choose. We're choosing k things from a set of n things. And later we'll get some sort of formula for this, but we're not quite there yet. Let's start with an example where we list all of the subsets of a 4-element set. So we know there should be 16 total subsets from some things that we did earlier in the course, but now we're going to list them by the size of each subset. Okay, so let's start with this maybe chart right here where we have k. So this is going to be the size of the subset. Then we'll explicitly list the subsets here, and then we'll count the number of such subsets, which means we're counting the binomial coefficient for choose k. Okay, so since n and k can both be integers here, that means k can be a positive or a negative number or 0. So let's look at this maybe really boring case where k is negative. So it's -1, -2, -3, -4, so on and so forth. Well, now think about this definition right here. It's the subsets with a certain number of elements. You can't have a negative number of elements. That's impossible. So I'll just say that there are no such subsets. I'll put NA here for not applicable, which means for choose a negative number will give us the number 0. So now what about 0-element subsets? Well, in fact, there's always a 0-element subset, and it's a unique 0-element subset, which is the empty set. And if we count up how many such there are, well, since there's the unique one, we just get the number 1. So this is really important, and this is actually true for any number, and that would be that if you take n choose 0, you always get the number 1. There's always a single 0-element subset. Now let's look at 1-element subsets. But that's pretty straightforward. You just make a singleton out of every element. Remember, singletons are always going to be like the only 1-element sets by definition. So we have the set containing 1, the set containing 2, the set containing 3, and finally the set containing 4. There are exactly 4 subsets like this. But now if you think of an n-element set, then there will always be n 1-element subsets for the same reason as this counting went here. You can just make a singleton out of every element. So in other words, we have n choose 1 is always equal to n. So at least we know those two values in general. Okay, so now let's go for 2-element subsets. So I think we can make some sort of systematic choice here. Let's do the ones that contain 1 first. So we could have 1 with 2, we could have 1 with 3, or we could have 1 with 4. Those are all of the 2-element subsets containing the number 1. Next, we could have the ones containing 2, 2 with 3, or 2 with 4. We won't have 2 and 1 because we've already counted that one. And then finally, the one last subset would be the subset of 3, 4. So notice there are 6 such subsets. And there's not a quote-unquote obvious way to write down a formula for 2-element subsets, and so we'll wait until we do this in more generality. Okay, so now what about 3-element subsets? Well, in fact, we can do that kind of in line with 1-element subsets. But instead of thinking about which element to include, we think about which element to leave out. So we could either leave out 1, leave out 2, leave out 3, or leave out 4, and that gives us 4 choices. So if we leave out the number 1, we get 2, 3, 4. If we leave out the number 2, we get 1, 3, 4. If we leave out the number 3, we get 1, 2, 4. And finally, if we leave out the number 4, we get 1, 2, 3. So it's counting just as we counted here, but instead of counting what to include, we're counting what to exclude. But there are 4 choices for everything to exclude, so we've got a 4 there. And just how we generalized these two, we can generalize this one as well. And that would be counting how many n-1 element subsets. And there are always n-1 element subsets. We're just talking about what we're including instead of what we're excluding. So now what about 4 element subsets? Well, we've got a 4 element set. There will be a single 4 element subset, and that will be the set itself. So 1, 2, 3, 4, so we've got 1. And then we can generalize this as well very, very easily. So how many n element subsets are there from an n element set? There will be 1, so n choose n is 1. Now what about 5 element subsets, 6 element subsets, and so on and so forth? Well, since we only have 4 elements to work with, we can never get a larger subset than a 4 element subset. So maybe we would also say that this is not applicable, or there are none, which means we get 0 such subsets all the way up there. And we could generalize this as well. N choose k is equal to 0 if k is strictly bigger than n. Or I guess if k is strictly less than 0 based off what we saw up here. So next up, what we'll do is reinvestigate this type of problem for the set 1, 2, 3, and we'll work towards a closed form of this binomial coefficient. So I misspoke on the last board. We're not going to look at subsets of 1, 2, 3. We're going to look at 3 element subsets of 1, 2, 3, 4, 5. This is right at the level where it would be too much to look where the numbers are larger, but this gives us some nice structure, like I said, towards a closed formula for n choose k. So here what I've done. I've made all 3 element subsets of 1, 2, 3, 4, 5. They're pretty easy to write out when the numbers are small like this, but any larger and it would be kind of a chore. And now we're going to build an array here. Let's notice that the number of columns in the array will be 5 choose 3. So let's maybe point that out. So number of columns. So like I said, that's going to be equal to 5 choose 3 because we're making 3 element subsets of a 5 element set. And then from there, what we'll do is build the entries of this table. And what are the entries of this table? Well, the entries of this table will be all 3 permutations of a 5 element set. So all 3 permutations, and I guess I should say of 5 objects. So of 5 objects. And then we're going to list these by 3 permutations that involve 1, 2, 3, 1, 2, 4, 1, 2, 5, so on and so forth. But the fact that we've got like a tool for doing this, we know that there's a closed formula for all 3 permutations of 5 objects. We had some notation for this. It was P of 5, 3, and that ended up being 5 times 4 times 3, or 5 factorial over 5 minus 3 factorial. So it's a descending product of 3 terms starting at 5. Okay, so now let's fill in the rest of this table. So here we'll have all permutations of the number 1, 2, 3. So we'll have 1, 2, 3, we'll have 1, 3, 2. Those are all the ones starting with 1. Next, we'll have 2, 1, 3, 2, 3, 1. Those are all the ones starting with 2. And then finally, 3, 1, 2 or 3, 2, 1. Those are all the ones starting with 3. Now we'll go down the line and do that for all of these. I'm not going to, in practice, fill out this whole table because it's just kind of a lot of busy work. But what we'll notice is that each of these columns has the same number of elements. So here we'll make all permutations of 1, 2, 4. So we'll have 1, 2, 4, 1, 4, 2. We'll have starting with 2, 1, 2, 1, 4, and then 2, 4, 1. Starting with 4, we'll have 4, 1, 2, and 4, 2, 1. And then so on and so forth. But notice that each column is made up of 3 permutations of 3 objects. It's just those 3 objects vary. So that means we can count the number of rows. So the rows would be like this row, this row, this row, this row, this row, this row. The number of rows is equal to 3 factorial. That's because we're taking 3 permutations of 3 objects. But now let's notice that we can calculate the entries 2 different ways. The way that we did before, or just by multiplying the number of rows and the number of columns. And given that, we can set up this equation for 5 choose 3 and solve for 5 choose 3 as 5 times 4 times 3 over 3 factorial. And again, that's just by noticing that 5 choose 3 times 3 factorial is this object over here, and then dividing by 3 factorial. Okay, so now we could totally generalize this to have all of the k element subsets here, and then all of the permutations of the entries of the k element subsets here. So here we would have n choose k columns, and then we would have k factorial rows, and then we would have pnk total entries, setting up a similar like division problem. So in the end, that brings us to the following nice closed form for n choose k. So I'll just put squiggle arrow here to say that we've just developed this. We have n choose k is equal to n times n minus 1 ending at n minus k plus 1 all over k factorial. So this descending product on the top is just this pnk. And then furthermore, let's notice that this is equal to n factorial over k factorial times n minus k factorial if k is between 0 and n. And often you're working with k values between 0 and n, so that's okay. And it's equal to 0 otherwise. And that's from reasons that we saw previously. Good, so now let's work through several examples. Now let's look at 2 examples. So the first one is fairly straightforward. Based off our definition, we want to determine how many 6-element subsets of the set containing 1, 2, 3 up to 10. So that'll just very simply, by the definition of the binomial coefficient, be 10 choose 6, which by definition is 10 times 9 times 8 times 7 times 6 times 5. So that's a descending product of 6 things on the top over 6 factorial, but I'll write that out as 6 times 5 times 4 times 3 times 2. And now let's cancel some things out. So we can cancel this 6 here with this 6 here. We can cancel this 5 here with this 5 here. We can take this 4 and this 2 and use them to cancel this 8. And then finally, we can cancel this 3 with this 9 down to a 3. And that leaves us with 10 times 3 times 7, or in other words, 210. Okay, so now let's ratchet up the complexity a little bit and see how many 6-element subsets of the same set are there with 2 or 3 even elements. Okay, so let's break this into 2 cases. So let's break it into the case where you have 2 even elements. But if you have 2 even elements, that means that you must have 4 odd elements. Okay, so that's pretty clear, because if 2 of them are even, I guess I should say exactly 2 of them are even, then the rest of them have to be odd. But if 3 of them are even, then the rest of them being odd means that 3 of them are indeed odd. Okay, so now we'll use the multiplicative and the additive property here, or principle, I guess it was. So to choose the 2 even elements, that will be 5 choose 2. because choosing the two even elements means that we're choosing two elements from the set containing 2, 4, 6, 8, 10, just the even numbers in here. But then choosing the four odd elements will be choosing 5, choose 4, because we're choosing 4 from the set 1, 3, 5, 7, 9. So again, still 5 element set that we're choosing 4 elements from. And now we take the product of these by the multiplicative principle, because we choose the even ones and we choose the odd ones, and then finding the total way of making those choices is multiplying them together. Then for 3 even, 3 odd, using the same kind of logic, we'll have 5 choose 3 for choosing the even ones, and 5 choose 3 for choosing the odd ones. And now all that's left to do is some arithmetic. So this turns into 5 times 4 over 2 factorial, which is just 2, and multiply that with 5 times 4 times 3 times 2 over 4 factorial, which is 4 times 3 times 2. Okay, so let's see this simplify. This 4 times 3 times 2 will cancel this 4 times 3 times 2. And then this 2 will cancel this 5 down to a 2. And we're left with 5 times 2 times 5, which is 50. And now let's look at this. We'll have 5 choose 3 times 5 choose 3. But that'll be 5 times 4 times 3 over 3 times 2, 3 factorial, and then squared, because that's just 5 choose 3 squared. But what do we get there? So here, this 3 will cancel this 3, this 2 will cancel this 4 down to a 2, and we'll have 5 times 2 squared, which is 10 squared, which is 100. So now putting these together, we see that there are 150 total such subsets satisfying this condition. Now we've got 2 examples based on the card game poker, and these are like classic counting problems. So our first goal is to determine how many 5-card poker hands there are in general. So that means we've got to choose a 5-element set from a set that contains all of the cards in a standard card deck, which would be 52 cards. So we have 52 choose 5. So in other words, we have 52 times 53 times 52, 52 times 51 times 50 times 49 times 48 over 5 factorial. So I won't multiply that out, but we get a fairly large number of 2,598,000 and then 960. So that's how many poker hands there are in total. So now we want to determine how many 5-card poker hands are flushes. Let's recall that flushes means that they have the same suit, and there are 4 suits, and each suit has 13 cards. So let's see, there are spades, there are hearts, there are diamonds, and there are clubs. Okay, so what we really needed to do is determine how many ways can we choose 5 spades, how many ways can we choose 5 hearts, 5 diamonds, and 5 clubs, and then really add them all together. But choosing spades will give us 13 choose 5, because we have to choose a 5-element subset of a 13-element set. It's just the 13-element set here is all of the spades. But it's going to be 13 choose 5 for all of these, because each of the suits have the same number of cards. So we have 13 choose 5 added to itself 4 times, or just 4 times 13 choose 5. So this ends up being 13 times 12 times 11 times 10 times 9 times 4 over 5 factorial, which is 5 times 4 times 3 times 2, nominally times 1. Okay, so notice I snuck the 4 in way over there. Now let's simplify these as we can. So we can take this 4 times 3 and have it cancel this 12. We can take this 5 times 2 and have it cancel this 10. And in the end, we have 13 times 11 times 9 times 4. And if you multiply that out, you'll get 5,148. So there are 5,148 total flushes, whereas there are 2.5 million total hands. So if we were calculating probabilities, you would see that the probability of getting a flush is quite low. Okay, let's do another poker example. Okay, so next up we're going to determine how many poker hands are a full house. So that's another type of poker hand, and this type of hand has a pair and 3 of a kind. So for instance, you might have a pair of 2s and then 3 5s. Or you might have a pair of aces and 3 queens. Okay, so by the multiplicative principle, what we need to do is determine the number of ways to choose 3 of a kind, and then also determine the number of ways to make a pair and take the product. But the important thing is that the number of ways to make a pair after making 3 of a kind is different than the number of ways to make a pair just kind of on its own. So we'll have to be careful with that. And you might say, well, does that mean that we should count this by making the 3 of a kind first and then the pair second, or vice versa? Well, in fact, it doesn't matter, and that's because of some relationships between the individual binomial coefficients, which you'll likely see on your homework exercises. So let's calculate the number of ways to choose 3 of a kind. So let's notice for each rank of card, there are 4 of them. So what I mean by that is that in the deck, there are 4 kings, there are 4 jacks, there are 4 aces, there are 4 5s. So we want to choose 3 of those 4. So that means building off of this, we'll have to choose 3 of a 4-element set. So let's say we want to choose 3 7s. How many ways can we choose 3 7s? Well, there are 4 choose 3 total ways. But we don't just want to, for instance, choose 3 7s or 3 9s. We just want to choose any 3 of a kind. So how many different rankings of cards are there? There are 13. So that means we'd multiply this by 13. Really, we're adding 4 choose 3 to itself 13 times. And that would be for choosing 3 aces or 3 2s or 3 3s or 3 4s, so on and so forth. Okay, so that's the number of ways to choose 3 of a kind. Now, after choosing that 3 of a kind, we need to make a pair. So how can we make a pair? Well, again, there are 4 of each ranked card, and we want to choose 2 of them. So there are 4 choose 2 ways to make a pair, if we're like choosing 2 of 4 7s or something. But now we can choose 2 of anything that remains. But how many remain? Well, there are 12 different ranks of cards that remain after making our 3 of a kind. So in the end, we need to take this product. 13 times 4 choose 3 times 12 times 4 choose 2. Then if you multiply this all out, which I won't go through the details, you can use similar strategies to what we did on previous boards, you'll get 3,744. Notice that's less than the number of flushes, and that makes a full house less likely to occur than a flush. And in fact, it is a higher ranked hand in poker. Okay, so now we're going to work towards some nice relations involving these binomial coefficients, and then look at some other applications. Now we're going to start looking at some of my favorite things, which are the relations between the binomial coefficients. So let's look at this nice one. In fact, this one can be used to define the binomial coefficients if we'd like to. And what it says is if we have natural numbers n and k is between 1 and n, then the binomial coefficient n plus 1 choose k is equal to n choose k minus 1 plus n choose k. Let's see why that is the case. Well, let's start with a subset A of 1 up to n plus 1. And let's assume that it has k elements. I won't write that down, but maybe I will write that down as the size of A equals k. The cardinality of A is k. Now, how many such A are there? Well, there are n plus 1 choose k. Okay, so now next up, we'll notice that A must satisfy exactly one of the following conditions. So I'll maybe put those conditions as these 2 blue dots. So n plus 1 could be an element of A. Well, that's possible because A is a subset, so that was sloppy. That should be a subset of that. because A is a subset of 1 up to n plus 1. But now if A contains n plus 1, then how many such A are there? Well, it has k elements in total. If it has n plus 1 in it, then there are k minus 1 remaining choices. And you can make those choices from 1 to n. So there are n choose k minus 1 possibilities for A. But what's the other case? The other case is that n plus 1 is not in A. But that means that all of the choices for elements of A are open. We can choose k total elements. But we can only choose them from the set 1 to n because we're not allowed to choose n plus 1. So that tells us that we have n choose k possibilities left over. And that's like a nice combinatorial interpretation of this setup. Or we could also establish this with a straightforward calculation. Let's do that as well. So I'll start with the right-hand side. N choose k minus 1 plus n choose k. So n choose k minus 1 is a descending product of k minus 1 terms. So n times n minus 1 all the way down to n minus k plus 2. That would be k minus 1 factors in the numerator. And then over k minus 1 factorial. Then we're going to add that to n times n minus 1 all the way down to n minus k plus 1. That is k terms in the numerator, and then over k factorial. Next up, we'll give these two a common denominator, and we'll do that by multiplying this first one by k over k. So that leaves us with n times n minus 1 all the way down to n minus k plus 2 times k over k factorial, and then plus this n times n minus 1 all the way down to n minus k plus 1 over k factorial. Now we have a common denominator, we can like put these together. But actually, let's maybe take this second term and rewrite it by putting the next to last term in. So we'll have n minus k plus 2 and n minus k plus 1. And now as we add these together, let's factor out this descending product from n to n minus k plus 2. So what does that leave us with? We'll have n times n minus 1 all the way down to n minus k plus 2. Then left over will be this k term here, and then this n minus k plus 1 term here. So we'll have k plus, because we have this plus sign here, n minus k plus 1. And then this is all over k factorial. But now let's notice that this k here cancels this k here, and we're left with n plus 1. And now we can put that n plus 1 over here at the front. So let's do that and maybe scrub this out in total. But that leaves us a descending product of k terms in the numerator starting at n plus 1 over k factorial. In other words, we have the binomial coefficient n plus 1 choose k. So there we have it. We have two arguments for the validity of this observation. First is a straightforward calculation, like I said, and the second one is this nice combinatorial argument where we take subsets of the set containing 1 to n plus 1 and partition them into two places. Okay, so now armed with this observation, I want to build something really nice, which you've probably seen before, called Pascal's triangle. So now we're going to use this observation that we just discovered two ways to build something called Pascal's triangle. And so you might recall that this is a triangle formed from a certain rule where as you descend, you add neighbors together. Well, that's exactly what's happening here. You would add neighbors together to get the term that's below and between those. So I've started with just like a tree of ones, but those ones are playing either the role of something choose 0 or something choose itself. Again, those are like 0 element subsets or subsets like that are full, if you will. Okay, so now we can start adding things together. So what should 2 choose 1 be? Well, 2 choose 1 is 1 choose 0 plus 1 choose 1. So that means you would add these two together to get this number right here. You would get 2. Okay, and then this is the 3 choose row. So here we have 3 choose 0 is 0, 3 choose 3 is 3. So what's 3 choose 1? Well, it's going to be the sum of these two above it, or 1 plus 2, which is 3. And likewise, this 3 choose 2 will be the sum above it as well. And now we can just descend all the way down. So adding the 2 above it will give us 4, 6, 4. Here we'll get 5, 10, 10, 5. Here we'll get 6, 15, 20, 15, 6. Okay, so how do you read this? Well, this row right here is the 6 choose K row. And for instance, this entry right here will be 6 choose, let's see, 0, 1, 2, 3, 4. So this is the 6 choose 4 entry. So that means 6 choose 4 is 15. Okay, so now let's investigate some more things involving these binomial coefficients. Now we're going to look at my favorite defining property of binomial coefficients, and that is that the coefficient of the monomial x to the n, y to the n minus k in the binomial expansion of x plus y to the n is n choose k. And the idea behind the proof of this goes like this. So if we take x plus y to the n and write it out as x plus y times x plus y n times, then we can easily count up the way to achieve x to the k, y to the n minus k. So let's write that down. So let's say we want to achieve x to the k, y to the n minus k. So really all we have to worry about is achieving x to the k. The y to the n minus k kind of comes along for free. Okay, so how do we do that? Well, among these n factors, we choose x exactly k times. So let's write that down. So we will choose x from k of these factors. So while we're doing the big product. So maybe we choose x here, we choose x here, we skip some x's, and then we choose x again until we've chosen k x's. But how many ways can we choose k x's from this list of n total factors? Well, that's exactly the definition of binomial coefficient. So multiplying this out, we'll get n choose k times x to the k, y to the n minus k. Okay, so that leads us to the very important formula, which is a lot more powerful than it might seem initially. And that is, if we take x plus y to the n, we get the sum as k goes from 0 up to n of n choose k, x to the k, y to the n minus k. Okay, nice. And now from here we can do lots of nice sum identities really quickly. So let's do those via some examples. Let's first determine n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n. So I'll do this two different ways. I'll do it with a combinatorial approach using subsets, and I'll also use this sum formula. So let's notice that this is equal to the sum as k goes from 0 up to n of n choose k. But that's equal to the sum as k goes from 0 up to n of n choose k times x to the k, where we've evaluated x at 1. And we've not only evaluated x at 1, but we've set y equal to 1 in this initial thing. And I would say that it's common to have this formula here with y equals 1. Okay, but let's notice that this is equal to x plus 1 to the nth power evaluated at x equals 1. But that's just 1 plus 1 to the n power, or in other words, 2 to the n. So what's another interpretation of this? Well, we could interpret this by our original definition. So this would be the number of 0 element subsets plus the number of one element subsets all the way up to the number of n element subsets. But that's all possible types of subsets. So that should equal the total number of subsets. But the total number of subsets from a fact that we had before was 2 to the n. So that would be another interpretation. Okay, so let's do one more before we end with some warm-up exercises for you to try. And that's the sum as k goes from 0 to n of minus 1 to the k, n choose k, 7 to the n minus k times 2 to the k. Okay, nice. So this seems like it might be really difficult, but if we just think about it as probably evaluating this binomial raised to a power at some certain numbers, it shouldn't be that bad. Okay, so let's maybe put all the powers of k together. We have minus 1 to the k and 2 to the k. So this will give us the sum, as k goes from 0 to infinity. We'll have n choose k minus 2 to the k, and then 7 to the n minus k. And now this looks exactly like this thing over here. So this is equal to the sum, as k goes from 0 to n, I should say. So that was infinity before, but that should be n, of n choose k, x to the k, y to the n minus k, where x is equal to -2 and y is equal to 7. But that's going to be equal to -2 plus 7 to the nth power based off this rule right here, but that's equal to 5 to the nth power. So that's a quick proof of kind of an identity that seems kind of gnarly. Okay, so let's end with some warm-ups for you to try. So here are 5 nice warm-up problems based off what we saw. So the first is to find the cardinality of the following set. So the set is all x in the power set of the set containing 1 to 12, such that the cardinality of x is equal to 6. The next is to answer how many poker hands have one pair and nothing else. Next, suppose there are 126 5-element subsets of A. What's the cardinality of A? Next, let's determine the coefficient of x to the 4th y cubed from the expansion of 5x minus 2y to the 7. And finally, simplify the sum as k goes from 0 to n of 6 to the k over 3 to the n times n choose k. And that's a good place to stop.